So we discussed the conformal gauge last time. Conformal gauge, and we finished solving some the equations of motion, right? So I remind you that the equations of motion are just the free equations of the following form. Where mu goes d minus 1. So it involves all coordinates in a kind of uniform way. So in the case of, well, either way we can split the solution to left moving and right moving wave. So, right plus x mu left, tau plus sigma, and we had some expressions for x mu that in the closed string case, so we have both closed string and open string case. So a closed string so that means periodic functions. Then we have x mu right, tau minus sigma is small x plus sigma and x mu left. So this is in the case of closed strings, and then we have also the case of open strings, which is basically so that means that x mu prime Neumann boundary conditions x mu prime at the ends of the string is equal to 0. And basically you have the same solution, but you replace alpha. So alpha and tilde mu is equal to alpha and mu. We also rescale p to 2p, same like we did while deriving the Lagrangians. So you look at the same solution, you just add up these two pieces, do this rescaling and set alpha equal to alpha tilde, and then you get the expansion that x mu is mu over pi t tau plus I square root of pi t sum all right, you get this expression, and the Poisson brackets of the oscillators is uniform for both cases, so the Poisson brackets are as follows. So we derived that a couple of lectures ago, right? So so this is the solution, but then we have the Virasoro constraints. Yeah, we'll discuss how to deal with the constraints in a moment. First, we'll discuss some questions related to the energy momentum tensor, to the conservation of the energy momentum tensor. So it follows from, so we have so in this type of theories where the energy momentum tensor is traceless, the conservation equation has the form d minus t plus plus is 0, right, as we discussed, because t plus plus t plus plus is this. So don't confuse the two t's, okay? The ones with indices is the energy momentum tensor. The just t without index is the tension. Yes, it's a constant. So so it follows from the just from the equation of motion for x that this guy satisfies this conservation equation, right? Because d plus d minus of x is 0. And such conservation equation actually implies the existence of infinitely many conserved quantities. In contrast to the usual conservation laws, means that there are conserved quantities. So this is supposed to be compared with, so this is a somewhat non-standard conservation equation, right? Because this should be compared with a typical conservation equation of the form d alpha j alpha is 0. So this is d plus g plus plus d minus g minus, which is let's put minus here. We have d plus okay, so J is some current. So usual conservation equation is that the divergence of something is 0, right? So it typically has two terms. So here the property, I mean, what makes this different is that there's only one term here. So it's kind of half of that conservation condition. And we'll now discuss these conserved quantities, so don't worry.
Why would there be infinity?
Because I'll show it now. So because now you can So this implies this, right? Trivially. Right? For any, so n, which I will assume integer, to be an integer. And that means that the conserved quantities coming from here are from, well, both in open and closed case. So, and these guys are constant. Right?
Would they be in involution? Is this an integral system?
No, they will not be in involution, so they will form some algebra, right?
Okay.
So, but they will form some algebra, not an abelian algebra. But yes, it's an integrable system in the sense that we've already integrated it anyway, right? I mean, we constructed all the most general solutions to the equations of motion in light cone gauge, right? So we've explicitly integrated it. It's kind of reduces to a free system, or expressed through a free system. So you don't need any fancy notions like integrability. It's just, yeah. Okay, so so you see, this trick you wouldn't be able to do if you had an equation of that form, right? So this is something special for this kind of conserved quantities, and this enhancement is typical of systems that, of course, have an infinite dimensional symmetry behind them, right? And we'll show that now. So, according to Noether's theorem, there should be some symmetry behind the LNs. So what is the symmetry behind the LNs? And the answer, this is a conformal symmetry. So LN, this is, has to do with conformal symmetry. And conformal symmetry here is kind of the remnant of diffeomorphism symmetry in conformal gauge. So these are the diffeomorphisms that preserve the gauge. So the gauge fixing is not complete, but there's something remaining. Well, the conformal symmetry here is that sigma plus goes to sigma plus, sigma tilde plus, sigma minus goes to sigma minus, sigma tilde minus. I mean, the idea is that the gauge is, maybe I should say that maybe this is Ts squared is e to the phi d sigma plus and sigma minus. This form is preserved under conformal transformation. So there's some additional factor that will appear. But again, all kinds of Weyl scalings are irrelevant. So, so this is formal gauge. Okay, so there are these transformations, and let us see how the LNs follow from this symmetry, right? So suppose, well, let's stick to this symmetry, and we will write it as sigma minus tilde equals sigma minus plus epsilon eta of sigma minus. So infinitesimal transformation. And by Noether's theorem, we may still use Noether's theorem to derive the corresponding conserved quantity. So by Noether's theorem or Noether's method, we should promote this guy to promote eta sigma minus to eta sigma minus and sigma plus. Right? This is no longer a symmetry. But to compute the conserved quantity, we should compute the first order variation with respect to the derivative of eta, right? I mean, single out the derivative of eta. And then, so when we do this transformation, we also say that x of sigma tilde, so the composition of x with sigma, is x tilde sigma tilde. So we view this as a some new function, new map, right? Which is in principle arbitrarily close to the original one, up to terms of order epsilon, right? Okay, so now we write that, and we want to substitute it into the action. By the way, if someone forgot, maybe I should write the action. So the action is T over 2 so this is the action. Right? So it should be clear that this is invariant with respect to these transformations, because the Jacobian coming from the derivative cancels against the Jacobian coming from the measure. Similarly for sigma minus. Right? It's a general property of such systems. So this is a free massless field. So typically such systems have conformal symmetry in them, right? By the same logic, at least classically. So this is a free classical sigma model, and classically such systems have conformal symmetry. So promote this guy. So now we have to substitute this change of variables and change of fields into the action. So we compute that d plus x mu is which is d plus tilde x mu plus epsilon d plus eta times d minus tilde x mu, and similarly d minus x mu is 1 plus so this is just a matter of doing the change of variables. So this guy is just a Jacobian coming from the conformal transformation, basically. This will cancel against the Jacobian coming from the measure, right? But the things that we are interested in is precisely these kind of terms, right? Which have the derivative with respect to the other variable that we've added here, right? I mean, it's already kind of clear from here that the conservation law will have this structure, right? Because the variation can only be proportional to the derivative of eta with respect to plus, right? Because the derivative with respect to minus, it's identically invariant. The action is identically invariant with respect to etas depending on sigma minus. So the variation will not depend on d minus of eta. So the variation will only have a term proportional to d plus eta. Therefore, the conservation law will be of this form. I mean, more exactly, the d plus t minus minus, right? There is of course the second conservation law, symmetric one, right? So maybe I'll write it that d plus t minus minus is also 0 by same logic. So now we compute the action. So this is a kind of Polyakov action in conformal gauge. So this is a I mean, plus maybe higher order terms that we don't care about, plus epsilon times I mean d plus eta. Yeah, d plus eta. So d plus eta times d minus right. So the first order variation is this guy, and so on the equations of motion we have to pick stationary configurations with respect to arbitrary transformations of the fields. So in particular with respect to this kind of transformation. So this the equation of motion therefore imply that d plus of which is the desired conclusion. Are desperately checking my calculation. Is there anything wrong with that? That's good. That's the right answer. So the upshot of this is that you can derive this conservation equation of the energy momentum tensor by studying conserved quantities coming from conformal symmetry of the action, just by the usual Noether method. And analogously, of course, the second conservation equation. So how is this compatible with the usual conservation equations of the energy momentum tensor, right? So just some remarks. Conservation energy momentum tensor. So this standard conservation equation has the form that d mu is this, right? Is 0. So from this we can derive a number of conservation laws usually. How do we do that? Well, we can contract t mu with various vectors. So suppose we have some psi nu is a vector field. It's a vector field. So we construct J mu is by definition t mu times psi nu. And let's check whether this is conserved or what are the requirements for it to be conserved. because, well, ultimately we want to have a conserved vector, right? Vector field. Then we can derive a conserved charge by integrating the zeroth component. So, so is this conserved, or what's the requirement? So, conservation. So we studied the derivative, the divergence of this guy. So there is a plus t mu d mu of psi mu. So this is 0 by conservation of the energy momentum tensor, and because the energy momentum tensor is symmetric, so we can rewrite this as 1/2 So we want this to be 0. So we see that in particular it's 0 if this is 0. So I mean that's a requirement. And what is this equation here? Killing equation, yes. So so we can construct a conserved current if we have a killing vector psi. So this is a killing equation. So this so we will require that. Killing vector. So for example, in flat space, what are the killing vectors in flat space? Yes, Poincare. So yeah, so the group of motions of flat space is the Poincare group, right? Or so rotations and translations you can derive from here by contracting with various fields. I mean, okay, but then we have the special case, like in this case we're studying here. We have the Weyl-Invariant theories. So Weyl invariance means that, well, Weyl invariance has to do with some metric on your worldsheet, right, or on your space-time, right? So we mean that we have a theory in flat space, but then we couple it to a metric in such a way that it's Weyl invariant, if we can do that. So in that case, so as we showed before, this means that the trace of the energy momentum tensor is 0. So traceless. So in this case, you see we can relax this requirement that it be a killing vector, right? And we can say that is what? So we want this to be 0, and we know that the energy momentum tensor is traceless.
Metric?
Huh? Yeah, exactly. So there's can be some function times, well, here the metric is a like I said, we are in flat space, so just eta mu, yes. So you see that the argument that d mu j mu is proportional to, in this case, t mu mu. So this is 0. Okay. So this means that Weyl invariance, if we can couple the theory to the metric in a Weyl invariant way, then this means that the original theory is conformally invariant. So so psi is a conformal killing vector field. So altogether, such set of xi's, right, psi nu a, forms a conformal Lie algebra. So Lie algebra of conformal group, or and in particular in 2D it is infinite dimensional, right? So and so the lns that we've derived is basically those conserved quantities related to the currents that can be constructed from the energy momentum tensor by pairing it with conformal Killing vector fields. That's the point. Yeah. So just again, in brackets, I'll note that there is also a notion of scale invariance, which is slightly slightly weaker. Scale invariance, which means that x mu goes to lambda x mu. If you just require invariance with respect to dilatations of this kind, this means that the corresponding psi mu is x mu. Then omega of x is just a constant equal to 2, right? So that means in turn that the mu g mu is t mu mu. And if this is a total derivative, then you can still form a current. So this is just a comment. So there are some other ways of relaxing the condition. So that means that the trace does not necessarily have to vanish, but it can be a total derivative. In this case, you can still have scale invariance in principle, without having conformal or Weyl invariance. Because in the case of special conformal transformations, this omega will not be a constant anymore, and this argument will not work. Okay, so the next topic is the next topic is the algebra of constraints. Yes, so the algebra. So that was the question, whether they're in involution. So they're not in involution, but they form some algebra. So Lie algebra of constraints, of Virasoro constraints. And I mean, as you can guess, because these are Virasoro constraints, so ultimately it will be a Virasoro Lie algebra. But I mean, we'll just derive that. So. In Noether's theorem, there are several steps in Noether's theorem. So first, the first says that if you have some symmetry, there will be a conserved quantity. So you have some Lie algebra G acting on the phase space. So this is a Noether theorem. Noether theorem. So then to each element of the Lie algebra, there corresponds some function HA that commutes with a such that HA with the Hamiltonian H is 0, right? Yeah, so X on phase space, meaning that it preserves all the right quantities, which more precisely are the symplectic form and the Hamiltonian. But I mean, we'll just assume at a physical level of rigor, we'll just assume it preserves all the relevant quantities. The second part, so this is the first part. The second part is that this map is a Lie algebra homomorphism, right? So this is a so that means that the commutator of A and B, again, which is an element of the Lie algebra, is mapped to the Poisson bracket of HA with HB, which therefore is, we can identify H commutator A and B. Right? I mean, a priori to the commutator, there is another conserved quantity which we can call H subscript commutator. But then the statement is that this is actually the Poisson bracket of HA and HB.
Can I ask why we can set the scalar variance? Why we can set the trace to be equal to some kind of derivative?
No, I'm saying if it is a derivative. If it is a derivative, yeah. If it is
in a different direction, basically. If we have this thing, then there is scalar.
Yes, there is scalar invariance, but not necessarily conformal invariance, because other conservation laws with other Killing vectors will not work. So this relies on the fact that the omega is a constant here in this argument. Yes, yes. Okay, so yeah, so we've derived. So in our application, these H's are the lns, right? And the commutator, so they correspond to some conformal transformations, and we know that conformal group is a non-abelian group. So there will be some non-trivial algebra. So so we have canonical momenta. So we have to work in phase space for this to make sense, right? So we have some Poisson brackets. So we have momenta, which are related to the velocities in the standard way. This is so this is derived from and the Poisson bracket is standard Poisson bracket, so x mu of sigma prime equals delta mu delta of sigma minus sigma prime. And the components of the energy momentum tensor that we want to consider have the form 1/4T this, which in kind of in brackets we know that this is the same as what we had before in terms of velocities. So now we need to compute the Poisson brackets of these guys. And the computation is as follows. So we need to compute T plus plus of sigma plus plus of sigma prime. Then there are many identical terms, right? I mean, so this is 1/4T squared P mu of sigma plus T times the Poisson bracket, so P mu of sigma plus t prime of sigma, comma p nu sigma prime x nu prime of sigma prime, and this is 2 t eta mu d sigma delta function sigma minus sigma prime.
Excuse me, why is it 4 in the denominator? Isn't it 16? Like,
No, it's not 16 because there is also a Leibniz rule for differentiation, right? So yeah, it's 16, but then this is squared, and you compute with something squared. So you once it doubles, because we kind of differentiate the square, one of the squares, and then it doubles because you differentiate the other square. Yeah, yeah. Of course, the kind of numerical factors are a matter of normalization, but still, yeah, it's kind of nice to keep track of them. So, so this gives the following answer: t plus plus of sigma plus t plus plus sigma prime here to get this answer, we use some identity, which is simple but still. For any function f of sigma, so if you have some f of sigma squared plus f of sigma prime minus 2 of sigma prime times this is f of sigma minus f of sigma prime squared d sigma delta function sigma minus sigma prime, and this is 0. Right, it's clear why 0. Yeah, because there's a second power here, yes. So this, so to prove this, just use definition of delta function, and then we apply this to this function f standing here. Right, this is f of sigma prime, and you can rewrite this in terms of f of sigma squared, f of sigma prime squared, so you get this nice algebra here. Okay, so let's continue. Okay, so we've derived this Poisson bracket, and accordingly we have a similar structure for the minus components. And t plus plus commutes with t minus minus. By the way, why is this anti-symmetric? I mean, the Poisson bracket should be anti-symmetric, right? So here you replace sigma with sigma prime. So it's clear why it's anti-symmetric. So? Okay, so I mean the delta function, your derivative of delta function is an odd function, right? So delta function is an even function, so derivative is an odd function. Okay, so this is this algebra for t minus minus or t plus plus is called a Weyl algebra. So here we have a sum of two Weyl algebras for t minus and t plus. So we have two copies of this algebra. They commute with each other. To get rid of the delta functions, we may integrate this with some test functions. So with test functions, so smooth. F of sigma, G of sigma prime, and define Tf is an integral of t plus plus f of sigma. Then you get the Poisson bracket of Tf is Tg is T of commutator F with G. Where by commutator we mean the commutator of vector field, yes? So this vector fields F sigma d over d sigma, G of sigma d over d sigma, which is F G prime minus G F prime d over d sigma. So these are vector fields because sigma is some kind of is a periodic variable, so these are vector fields on a circle. So these are vector fields on a circle. So these are periodic functions. F and G are periodic functions. And that's why this Weyl algebra is the Lie algebra of diffeomorphisms of the circle. Okay, now if in place of these test functions we take our exponentials, which form a basis of functions on a circle, right? So we can define Lm as t exponent of I and sigma. Then from here, we get that Ln with Lm is Lm plus n. So this is the algebra, right? So they're not in involution, they form some algebra. So analogously, we could define components of similar conserved quantities related to the t minus minus. So we could define t tilde f, which is t minus minus. Here I really mean mostly the closed case, so I'll put integration 0 to 2 pi, and then ln tilde, just t tilde e to the I and sigma, and then they have same algebra, they form the same algebra, same Lie algebra. Star. So indeed, what we've discussed so far has to do with conformal transformations for the closed string. So when we derive these conserved quantities, we use the fact that we can independently reparameterize sigma plus and sigma minus, right? But in the case of open strings, when we do our conformal transformations, the action formally looks the same, so it's invariant under conformal transformations, but we should respect the boundary conditions, right? So that means that sigma equals 0 pi is mapped to sigma tilde equals 0 pi. And our map sigma versus sigma tilde, or from sigma to sigma tilde, can be rewritten as tau tilde plus minus sigma tilde. So this is sigma tilde plus minus is f plus minus of tau plus minus. That's the original transformation we had. Yeah. So I now rename these functions as f plus and f minus, and I rewrite this in terms of tau and sigma. So let us set let us set sigma equals 0. Should be mapped to sigma tilde equals 0. So that means that tau tilde is f plus minus of tau. So that means that f plus equals f minus, right? I mean, they're both equal to tau. So the transformations that leave the boundary at sigma equals 0 unaltered have f plus equals to f minus. So you have to do the same transformation on sigma plus and sigma minus. Analogously, if you set sigma equals sigma tilde equals pi, then you get that f, and let's call this f of tau plus 2 pi minus f of tau equals 2 pi. So that means f of tau is tau plus, where this is a periodic function. Explicitly, you can also rewrite. Okay, this is just some rewrite in terms of tau and sigma. So And so there's a single function involved, function f tilde. And these transformations, also one can check that they preserve the boundary conditions, right? So we have to, so just as a consequence, so for example, dx mu over d sigma equals 0. This is dx mu over d sigma tilde, d sigma tilde over d sigma equals 0, plus dx mu over d tau tilde. And from here you check that this is 0. So the vanishing of dx mu over d sigma implies the vanishing of dx mu over d sigma tilde. So it's kind of consistent. And in this case, there is a single set of, therefore there should be a single set of conserved quantities, right? Because we only have a single function to make variations of the Lagrangian with. Right, so, and it has the form that, from 0 to pi. So this is a single copy of the Witt algebra. And we can write out these generators explicitly in terms of our oscillators. So again, the difference between the open and the closed string case is that in the closed string case, kind of everything is doubled. So in particular, this algebra of invariance is turns into two copies of this algebra. So kind of technically, it is simpler to discuss the open case, because the closed case basically results in doubling of everything. So let's write out these LNs in terms of the oscillators. So the LNs for all cases either closed or open, the LK has the following expression: 1/2 where by scale product I mean just scale product in Minkowski space. Yes, so this is A mu B nu eta mu nu. So just not to write the Minkowski index, I'll write the brackets. Okay, but here we've secretly introduced also the variable alpha 0. So before our oscillators were only for alpha 1, alpha 2, etc. Here we also have alpha 0. So alpha 0 is the shorthand for momentum. So this is, by definition, this is P mu case of open strings, and is P mu by definition case of closed strings. So this is just notation, just to write it in a single sum like this. But in principle, you can, so we have this expression for t plus, which is, so for example, t plus is t d plus x mu squared, right? This is, say, t d minus x mu squared. Then we have expressions for x mu that we wrote out at the beginning, right? Solutions of the equations of motion. They involve alphas and p and x. Well, x will drop out, but p will stay. So you just differentiate, substitute here, integrate, and you get some. You get a sum which has sum over oscillators plus some term involving momentum, right? So just to write it as a single sum, we introduce this notation. But somehow these funny factors of 2 are important later on. So that's just why we discussed that here. Okay. And now we have our favorite Poisson brackets of the oscillators, which are alpha m mu, alpha n mu minus im delta m plus n eta mu. In closed string case, here one also has LK tilde, okay, which has the same expression in terms of alpha tilde. And then the alpha tilde have the same commutation, Poisson brackets. So now let's compute the Poisson brackets of LKs. So on the one hand, we use this general Noether's theorem that the Poisson bracket should go to the conserved quantity derived from the commutator of vector fields, and we computed the commutator. On the other hand, we can just directly check it by computing the Poisson bracket of L's. So this is so I'll compute LK with LL is naively, if you just compute the Poisson bracket, it has n times alpha k minus n alpha L plus n. Then I do a change of variable, n goes to k minus n. So this is I sum over n k minus n. So this is 1/2, and we write this as 1/2 the same thing plus n to L plus k minus n. So there are some small manipulations you do with this thing, and then you find that this is I over 2 k minus L times sum of alpha k minus n, alpha L plus n, sum over n. So this is I k minus L, L k plus L. So this is a small calculation. So this is an infinite dimensional Lie algebra, but it has a finite dimensional subalgebra. So the important finite dimensional subalgebra, kind of important subalgebra is furnished by the generators L0, L plus L0, L plus minus 1. So here the brackets are L0 with L1 is minus 2i L1, L0 L minus 1 is 2i L minus 1, and L1 with L minus 1 is 4 for I L0. And then we also recall the reality properties of the oscillators. So the reality properties were that alpha n star is alpha minus n. So that means that Lk star is L minus k. So L1 star is L minus 1. So this defines a real form of the SL2. So this is so this is some SL2 Lie algebra. So the real form is SL2R, which is the same as there are different names for it. So I mean, so 1 2 S U 1 1. So and so why is it an important subalgebra? Or I mean, what does it correspond to? Hmm? No, it's not SU2, it's SL2R. But I mean, from the point of view of the geometry, conformal geometry.
Just fractional linear transformation.
Yeah, that's right. So these are just the usual so dilatations, translations, and special conformal transformations. So this is the two-dimensional analog of the general conformal transformations that you have in any dimension. Yeah. So in any dimension you have a conformal group. If you kind of naively reduce it by a dimension, you get this. Just on top of that, in 2 dimensions, you have those infinitely many other ones. Okay, so this is an important finite dimensional algebra. Maybe as some kind of curiosity, you could try to find other finite dimensional subalgebras. I mean, other means involving other generators, not L0, L1, L minus 1, or not all of them at least. Okay, and now we'll do the quantization of this. So basically we need this formula there. So we want to discuss what happens upon quantization. Because the sort of difficulties that arise in quantization, they arise in various other contexts in quantum theory that we will need later on. So the quantization just amounts to replacing the Boson brackets with commutators. So this is in this case it's rather simple, right? So we just the small x's and small p's commute to I delta mu, and oscillators commute to as follows. Notice that when we quantize, there is an extra factor of I that appears. So it appears here and disappears here. So the quantum version of these LKs is you just normal order them. So yeah, before normal ordering, we should say that, well, these oscillators come in pairs. M is conjugate to minus M, right? So we make some agreement that alpha and mu with M positive, these are annihilation operators. and alpha minus mu, then positive. These are creation operators. And then the notion of normal ordering makes sense, right? So normal ordering means that you place all annihilation operators to the right of creation operators. And then we normal order this sum here. Well, actually, the only element of this set where we need normal ordering is for L0, right? Because for L, K0, K equal to 0. Because for K not equal to 0, these guys commute. So it doesn't really matter. But for K0, we use normal ordering. And now we want to compute the quantum algebra of this LKs. So that means that instead of Poisson brackets, we want to compute commutators. So we want to compute for such quadratic combinations, so when we compute a commutator of two such quadratic combinations, it will be a quadratic combination, right, of alphas, clearly. But so why can it possibly be different from the Poisson bracket? I mean, it looks like technically it's almost the same as computing the Poisson bracket, if you think about it, right? So why can it be different? Well, so the point is that suppose this is just a general remark. So suppose you have a set of oscillators that I call AI, some oscillators. So I mean AI dagger and AI. And suppose you're computing quantities of the form AI dagger AJ with AK dagger AL. Then, I mean, just directly computing it, you find that the right-hand side is automatically normal ordered. Yeah, I mean, the possible difference from computing Poisson brackets can come from the fact that the quadratic combinations in the right-hand side are not normal ordered, right? And in case of Poisson, when these were classical variables, we could just permute the two factors without any effect. But here we have to take into account the commutation relation, right? So let us think where this situation occurs. So for example, if you have also two quantities of this type, they commute automatically to a normal ordered form, right? So the problem arises if you commute quantities of the type AI AJ with AK dagger AL dagger. Okay. Again, here I'll just write the answer. So you have some normal ordered term plus and this is not normal ordered term, this one, right? So if we were computing Poisson bracket, we would get exactly the same expression, but now then we just swap the L's, or if we wish, the A's, I mean. This is just a calculation the precise form of the answer doesn't matter so much. What matters is that these guys are not normal ordered, so you'd have to swap them and get extra terms. So the question is, we want to commute these guys, so do they have terms of this type? Yes, they do have terms of this type, but the nice thing is that there's only a finite number of such terms. So this problem occurs only in a finite number of terms, and these are terms of the type. So suppose k greater than 0, then the part of the sum that has this kind of terms is 1/2. So sum n from 1 to k minus 1, alpha n, alpha k minus n. Right? You see in these terms, this guy is a annihilation operator, and this guy is an annihilation operator. So both have positive index, positive subscript. And accordingly, for negative k, you have a piece where both are creation operators. So we want to compute delta Lk. So these are finite. It's a finite sum. That's kind of the improvement. So now we want just to commute these guys, you'll get the following answer that. So this is a 1/2 e from 1 to k minus 1 p this kind of sum. And these guys do not commute with each other only if m plus k equals is 0. So plus k equals 0. So in all other commutators, there's no problem, so there's no extra terms. So let's set m to minus k and see what this is. So here we set m equals minus k. And then, so you have 1/2 p alpha p minus k alpha k minus p plus k minus p alpha p alpha minus p. And then here you do a change of variable. P goes to k minus p, and you find that this is 1/2 k minus p times alpha minus p alpha p plus alpha p alpha minus p. P from 1 to k minus 1. So you see this term is already normal ordered. So this term is not normal ordered. We just normal order it. So we swap the two factors of alpha. We write that this is alpha p minus p plus d times p. Right, so p comes from the Poisson brackets of the oscillators. By the way, I wrote it incorrectly, yes, so there should be a factor of m here. Yeah, I mean, it matters. Remember, these oscillators are normalized in such a way that there is a factor of m. And that's the factor of p here. And d is just because you have a sum over d identical terms coming from the scalar product. So this means that this is a normal order thing, plus d over 2 sum of p times k minus p. P from 1 to k minus 1. And then you do the sum, and this is d over 12 k cubed minus k. So that means that the algebra has the following form. The final algebra, the quantum algebra, k with L is k minus L times Lk plus L plus delta k plus L d over 12 k cubed minus k. So delta k plus L, because this extra piece only arises for when m is equal to minus k. So that's why we have the delta k plus L there. Okay, maybe just again so that's the Virasoro algebra, right? So that's the Virasoro algebra. Comes from the Virasoro constraints, so it's, I mean, of course, related. And this is the famous Gelfand-Fuchs cocycle. So these central extensions, like the one that arises in the Virasoro algebra, can be understood in terms of what is known as a cocycle, right? So cocycle is a map. So cocycle, this is a map from Lie algebra cross Lie algebra to complex numbers, satisfying the some properties, such as, well, first of all, it's skew symmetric. So omega of AB equals minus omega of BA. And secondly, there is a property that ABC plus cyclic permutations is 0. And the non-trivial, so there's also a notion of trivial cocycle. Yeah, so given omega, one can construct a new algebra G tilde, where the commutator of A and B in G tilde is the commutator of A and B in G, plus omega of A and B times some new element which central element. That means it commutes with everything. So if omega of xab is some function of commutator of A and B, then this is trivial cocycle. That means that the new Lie algebra just splits as into direct sum. You can just redefine your generators in such a way that it's just a direct sum, so the central term doesn't appear anywhere. I mean, you can easily prove it. So just to finish, I'll just say what this is in the case of the Virasoro algebra. So in Virasoro algebra, omega, so Virasoro, or that Gelfand-Fuchs cocycle corresponds to omega of Ln with Lm equals delta m plus h of m. So you can check that h of m linear. This is a trivial cocycle. But h of m cubic is a non-trivial one. So, and there are no other ones. So this trivial cocycle kind of is important too, because it just corresponds to a shift of L0 to L0 plus constant. And it will often be useful to do this shift. So trivial cocycle means you just redefine your generators, and formally you get some other form of algebra, but of course it's isomorphic.
Is this any function f?
Yes, yes. Well, linear function. So I mean, just like here, omega f is g to c. Yeah, linear function. Omega is also linear, bilinear. So yeah, it's kind of okay. So this is the Gelfand-Fuchs thing. Okay, and just last problem related to this, like homework problem, is to show that this, so you can think of the f and g, fg belong to the algebra of diffeomorphisms of the circle. So just some functions on the circle, periodic functions. Then show that this central, this cocycle on this f and g has the form d phi f prime g2 prime minus g prime f double prime. Okay, this is the basically if you take in place of f and g the exponents, you get the m cube thing. And then there is a more complicated problem. Show that this extension can be lifted to the group. Lift to the group, to the central extension. Of the group. Diffeomorphism S1, so central extension is called diff with hat of S1. Here there is also a cocycle which is called Bott cocycle. G times G goes to E1. So this is G. And has the following form. So this is to show that this has the form phi psi. So phi psi are two maps of the circle to itself that are diffeomorphisms. This is the exponent of 1/2 integral logarithm of phi composition psi prime times d logarithm psi prime. Okay, this is a Bott cocycle. This is the task. So in this extended group, so G hat, composition is defined as this is by definition, this is a composition of phi and psi. Okay, so given the group diffeomorphisms, you can form another group which has a U1 factor here. So with this kind of multiplication, so you can show that this is to have associativity. There is some property of B that B has to satisfy for this to be associative, and then you can prove that this satisfies this property. So this is. And this is the infinitesimal version of that, right? So if you find psi are close to the identity, you get this thing. Okay, so, and that's it for today.